70th birthday conference, yes, 70th birthday election conference here. I came here, and that was the time the bust of Harishchandra was unveiled by Mrs. Harishchandra, and it was wonderful at that time. I was also, I had the opportunity to talk here at the time too. And when I was leaving, it seemed to me that the positive look from Harishchandra's burst, it looked as if it wanted me to come again. This is the occasion. So great. In Harishchandra's centenary celebrations here at the Harishchandra Research Institute, and taught to you in this workshop on some aspects of the theory of representations of a connected real semi-simple Lie group. Discuss also some aspects of the theory of characters, invariant eigendistributions, more particularly about discrete series representations, that is, irreducible unitary representations with square integrable matrix coefficients. The group G will be assumed to be connected real semi-simple Lie group with finite center. A representation pi. Oh, in case you want me to stop and say anything, or if you have some question, please do not hesitate to interrupt me, okay? Of G in V. V will be a complete locally convex topological vector space which is housed of complex and separable as usual. There is the usual notion of continuity of the action of G on V, irreducible if the only closed subspace of V which is stable under the action of G is V itself or 0. A vector V is differentiable if the function x going to pi x acting on V belongs to C infinity G V. Denote by K a maximum compact subgroup of G. A vector is K finite if it belongs to a finite dimensional subspace.
Whenever you define this, V is a Banach space, suppose. Whenever you define smoothness.
Well, you can think of whatever you want, like you can think of Hilbert space.
Locally convex space, you have to take this normal seminar or take the definition.
But a continuous linear, take any continuous linear form which is continuous with respect to the seminorms which define the topology there.
Which is stable under the action of K on the space of all K finite differentiable vectors. There is a Lie algebra action of the Lie algebra G of the group G. You can see the action described on the screen here. K is a fixed maximal compact subgroup of G. A representation.
So is K finite vector is not differentiable, or you can take the differentiable from vectors and then take K finite.
Take differentiable vectors and take K finite vectors. But
The question is like, is any K finite vector is differentiable?
I assume I think so. Right.
Pi of G
Sure.
on a hill
That's questionable. It's very
V is said to be admissible if the span of the K-finite vectors is dense in the L2 sense, and the multiplicities of irreducible K modules are finite, and when you compare the multiplicity to the dimension of the irreducible, when you compare it, that proportionality is bounded uniformly.
By the way, the statement that the multiplicities are bounded, when you compare it with the dimension of the irreducible K representation, they are uniformly bounded. I don't know where I took this screenshot, but so far in the lectures we had, there was no assumption that it's uniformly bounded.
That proportionality is bounded uniformly.
You know, we can see the video.
Harishchandra?
Can you go back to the slide?
Quotient theorem or subrepresentation theorem, because you get this estimate for principal series by Frobenius.
Oh yes, okay.
Proportionality is bounded uniformly. Harishchandra introduced the notion of quasi-simplicity of representations to exclude some pathological behavior, and also a notion of infinitesimal equivalence among them. I welcome you to this wealth of information in the next video.
A small clip.
But just tell you this theorem that for unitary representations of G, unitary equivalence and infinitesimal equivalence are the same. There is a reference to Warner here, and I suspect that I must have come across this screenshot by looking at some notes of Trombi. I think Peter Trombi at University of Utah is a student of Gott Warner.
Well, I was told by Graham Milch that that's not correct, that he's not a student of Warner rank. But I still suspect that I must have come across the screenshot in some notes of Trombi, because Trombi once told me that he got the two big fat volumes of Gott Warner for $1 each in a garage safe.
Yeah, I mean, Peter Trombi is definitely of Indian origin. He always claimed that mathematically, that his teachers were Rangarao and Ganguly, and of course Varadarajan did joint work in immediate.
Let me see if I can bring you a video of David Hogan, where many of these notions are beautifully explained. When I meet him next week, I must.
The top. Okay. Any questions or comments?
I have a question, if I may.
Of course.
In this conclusion, where does admissible fit in?
So admissible is a historical accident. Let's see if I can make and oops, that wasn't right. So what Harishchandra proved Well, admissible means the restriction to this compact group K of R has finite multiplicities. And Harshchandra proved that quasi-simple, which is clearly a nice natural definition, is equivalent to admissible. And this direction is very easy, and this direction is one of Harshchandra's many giant theorems. So, in my opinion, quasi-simple is what people should always talk about. The fact that it's the same as admissible is a really important theorem, but it's not what one should think of as the definition. So that's what happened to admissible.
Okay, perfect, thank you.
Okay.
And I have another basic question that I just want to get the answer to. When is Z of G that you defined earlier, when does that coincide with the center of the enveloping element?
Okay. That's another great question. So I said the Z of G was the fixed points of the real group on the enveloping algebra, and that's equal to the center of the enveloping algebra, if and only if this group G of R is what's called in Harshchandra's class. What it means.
The group G belongs to the Harshchandra class if the Lie algebra G is reductive and the adjoint is contained in the connected complex adjoint group. The analytic subgroup of G defined by the bracket of G with itself is closed. The group can be written as a product where V is a vector group and the other factor is the kernel of all continuous homomorphisms of G into positive reals. Fix a maximal compact subgroup K of G. There is a Cartan involution on the group and on the Lie algebra. On the group, the fixed point is the maximal compact K. On the Lie algebra, the fixed point is the Lie algebra German K of the maximal compact K. The -1 eigenspace for the Cartan involution theta is denoted by German P. We extend, I say German K, German P, but as Raghunathan pointed out, it's Gothic. Germans don't say German G or German K, they say Gothic letters. The killing form of the semi-simple part of G to all of G to be non-singular G invariant symmetric bilinear. K and P are orthogonal. The negative of the bilinear pairing between x and theta x is positive definite and gives rise to a norm. All Cartan subalgebras have the same dimension. That number is denoted L, the rank of G. Consider the expression determinant of add x minus 1 plus t. Rather, the determinant of the operator on the Lie algebra, then endomorphism on the Lie algebra. The coefficient of t to the power l is denoted dx. Dx is regarded as a function of the group. A point is singular if dx is 0, otherwise it is called non-singular or regular. This set of regular points is an open set. For a Cartan subalgebra L, the centralizer L in the group is the Cartan subgroup. Intersect L with the open set of regular elements of G denoted by L prime. That psi alpha is the symbol for a character corresponding to root alpha. If a root takes only real values on the Cartan subalgebra, then you call it a real root. If it takes only imaginary values, you call it an imaginary root.
Well, this morning, Raghunathan told you that for a compact semi-simple E group, all the roots, they're all real they're imaginary on the Lie algebra of the Cartan subgroup, compact Cartan subgroup. So, but when you have a non-compact real semi-simple E group, there are Cartan subgroups which are non-compact. They have a vector part, and some roots may be 0 on the compact part, and those roots will be real.
There are only finitely many conjugacy classes of Cartan subgroups, and every conjugacy class contains one which is theta stable. When it's theta stable, you can write it as this product. If G admits the compact Cartan subgroup, then they will all be conjugate. Complexifications are denoted with a subscript C. If mu is a linear form on the dual of the Cartan subalgebra, if mu is a linear form on the complex Cartan subalgebra, complexification of the Cartan subalgebra, this expression e to the mu h defines the character on the Cartan subgroup L if mu has some integral properties. This expression delta Lp is the famous Weil denominator. Normalizer modulo the centralizer is the Weil group. If you do it without going to the complexification, that is WL, that is not the same as WLC, which you will get after doing the complexification. A linear form lambda is regular if it does not vanish on the roots. It is integral if 2 lambda alpha by alpha alpha is an integer for every root alpha. You have the usual Iwasawa decomposition G equal KAN.
Yeah. No.
Previous slide.
You want light?
Previous slide.
Oh, previous slide.
So this way so this expression delta L what is this?
Delta LP is no. What's your question?
What is that?
No, there is this Bell character formula for the character of an irreducible representation. So it's given as the quotient of, so in the numerator it involves the highest weight, some expression involving some alternating expression which involves the highest weight. And the denominator does not involve the highest weight, but it's a fixed sum, alternating sum of the sum of the positive rows. So that's what it is.
By alpha alpha is an integer for every root alpha. A real parabolic subgroup and real parabolic subalgebra the Q intersected with the cotton evolution theta applied to Q is denoted M1, that is called the Levy part of the parabolic subalgebra. Center of M1 intersected with P is denoted C. Inside the group M1 you have the subgroup, closed subgroup M. That is the intersection of the kernel of all the homomorphisms into positive real numbers. The Lie algebra of the group M is this German M. M plus C is equal to M1. M plus C plus N1 is the lambda for S. The one is called is described on the level of C. These criteria, the most satisfactory description would be to look at it in the framework of. Well, if you use this screen, you have, I'm describing the Laplace decomposition. You start with the sigma there is the set of simple roots, and you take a subset of the set of simple roots, and there is something called Laplace decomposition for the parabolics associated with that. That's what I'm describing there. And then, if you take the element of the enveloping algebra, it acts from functions on the group, but there is an adjoint action which is defined here for distributions. And so, we have to figure out why the volume went down. So, So here, the Harishchandra homomorphism this morning, we had a beautiful treatment, which is explanation given by Milicic. So the same thing. So you have a Parthasarathy algebra and a set of positive roots, and you define the sum of all the root spaces corresponding to the positive roots. The point that decomposition, Parthasarathy algebra plus sum of positive roots, root spaces corresponding to positive roots, plus root spaces corresponding to negative roots. That has, if you use that decomposition with a pointary Beckhoff weight, so you get that decomposition of the enveloping algebra into certain subspaces, and you take an element of the enveloping algebra, you project to the enveloping algebra, the Parthasarathy algebra. Yeah.
That's only there.
So, when you project to the enveloping algebra, the Parthasarathy algebra, and restrict your attention only to the center of the enveloping algebra, you don't always get invariance under the while group there in the in UH. You have to do a small correction of homomorphism. The use of the positive system of roots there, did they do it? Yeah, I don't know what happens. Simply executes this correction. The second step involving the same. But I'm also saying here that
we should not spend too much time with this structure theory facts. There's a lot of things to say in the coming lectures about the short space, cusp forms, matrix coordinates of discrete series, Harshchandra's theorems, and yeah. So I was saying that you should, I should not be talking too much about this. So anyway, since it was explained to you this morning, I'll skip on the next slide.
This is the algebra which does a correction to make the image directional homomorphism well grouping it. I want to get back into the notation used by V.S. Parthasarathy in his notes to be consistent. In the last two slides, they were looking quite different, all those symbols. If you have an equal rank subalgebra of G, say M, then there is a Harshchandra homomorphism from the center of the enveloping algebra of M. You see this mu GL, that is the Harshchandra homomorphism in Parthasarathy's notation that you see in this slide here. One is mu ML, where M is the equal rank reductively subalgebra of G. It is the same map as this mu GL except that G is replaced by M. There is another map from the center of the enveloping algebra of G to the center of the enveloping algebra of M. That is denoted mu GM, that is with the L replaced by M here. Be happy that mu GL can be factored as you first apply mu GM, then follow it by applying mu ML. That is the same thing as mu GL. What are all the homomorphisms of the center of the enveloping algebra into the ring of complex numbers? Rather into the algebra of complex numbers. Take an element Z of the center of the enveloping algebra, apply the Harshchandra homomorphism to get a polynomial on the dual of the Cartan subalgebra, evaluate the polynomial at a fixed lambda, the same lambda for all the Z. That is the homomorphism which we denote by chi lambda, and any other homomorphism is of this type. Chi lambda is equal to chi lambda prime if and only if lambda and lambda prime are in the same orbit under the Weyl group. Chi lambda is called regular if lambda is regular. Would be a finite dimensional Hilbert space. Suppose the group K acts on U both from the left and from the right, and that the two actions commute with each other. The action on the left is denoted by tau 1. The action on the right is denoted by tau 2. A function from the group G to the vector space U is said to be tau spherical if f of k1 x k2 equals tau 1 k1 applied to fx and on the right applied to tau 2 k2. Let me say that again. Take a group element x belonging to G. Take two group elements K1 and K2 belonging to K, capital K, the group compared to K. Given the value of the tau spherical function f at x, how do you describe the value of f at k1x, k2, that is described by the right side here. When we wish to recall this property, we simply say f satisfies equivariant conditions with respect to the action tau. If f is smooth and it satisfies the k equivariant condition, and also if you know that the function is z finite, where z is the center of the enveloping algebra, then these functions are analytic. To give you an example of such a function which arises in a natural fashion from irreducible representations of the group G, suppose pi is the representation of the group G on a vector space, infinite dimensional vector space V. Take two finite dimensional subspaces W1 and W2 inside V, both of which are stable under the action of K. So they are both K finite submodules of V. K finite K submodules of V. For the vector space U in the definition of tau spherical, we take it to be the space of all endomorphisms from W1 to W2. Sorry, the space of all linear maps from W1 to W2. Given a group element X belonging to G, the corresponding linear map from W1 to W2 is illustrated by this diagram here. First, take the inclusion W1 to V act by pi x and then project to W2. That'll, any questions?
Double interpretation means simply tau 1 is a interpretation and tau 2 is a interpretation.
And the two actions,
And from left and right.
yes, the two actions come. Tau,
Two options.
okay?
What is
The W1, W2 is an example coming from the irreducible, the example of a tau spherical function coming from an irreducible representation of G. So there W1 is a k-invariant subspace, W2 is another k-invariant subspace. Or could be the same k-invariant subspace.
Satisfy the equivariant condition, and it will also be z finite. The number of linearly independent tau spherical functions annihilated by a fixed ideal in the center of the enveloping algebra with codimension M. This data gives an estimate for the number of linearly independent tau spherical functions. W is the order of the well group of the ambient well group, and M here is the codimension. The proof of this theorem will use the KAK decomposition of G. So essentially the tau spherical lives on A, and it will use differential equations on A. The symmetric algebra of the Cartan subalgebra contains the well group invariants, and that is precisely the image of the Harish-Chandra homomorphism. As a module over the algebra of well group invariants, the polynomial algebra is a free module of rank equal to the number of elements in the while group. That is the reason why this number W appears on the right in this inequality, in this estimate. This theorem has an important corollary for irreducible unitary representations of the group G. Let delta be an irreducible k-tag. The multiplicity of delta in an irreducible unitary representation omega of G is finite, and the theorem implies a bound for this multiplicity given on the right side. Well, here you can see that uniform bound C, which I mentioned about in another slide. The W to the power 1/2 is the constant C. Put a proof of this in the next slide. Usually this is given as an exercise or just simply left out as easy. Of course it is easy. Here is the easy proof of that corollary using the theorem. You can see that it's a very short proof. It's a good idea if you don't look at it first, but try to work out yourself and then come back and compare. If pi is an irreducible unitary representation of the group G acting on a Hilbert space H, so like this, I'm trying to make some remarks and conclude that the operator pi f is of trace class using that Pareto theorem and corollary just mentioned in the previous screen. And if f is a C-infinity function with compact support, you can define this operator integral over G fx pi x dx. That is, you can integrate pi x, multiplying it by a compactly supported function. How do you define this operator? Take a vector v in the Hilbert space. So this operator pi f, I have to tell you what it does to this vector v. I think everyone defined this operator, so I can skip a few seconds to this. Defining the distribution character of an irreducible unitary representation, that is an invariant eigendistribution, and if chi omega is the infinitesimal character of omega, or chi pi is the infinitesimal character of pi, then this distribution will also have the same infinitesimal character when you differentiate by elements of the center of the enveloping algebra. You want me to go back a little or proceed? You don't really need the fact that the matrix coefficients of pi are square integrable. What matters is the L1 norm of this omega SF. I show you a study of invariant eigendistributions begins by restricting attention to smaller invariant open sets, the operator pi. So this operator pi f, I have to tell you what it does to this vector v. If you take another vector w, I will tell you what is the result of this when you take inner product with w. For that, you look at the integral, the integrating pi x, multiplying it by fx, and integrating over g. Look at that look at the operation. Take your two vectors v and w, take the inner product of pi x v with w. Thus now, the scalar value function on the group, multiply that function by this compactly supported function fx and integrate. That is the inner product of w with the operator pi f applied to v. So what we have done is we took, I think some questions can be reserved
So later informal discussion, because I may, I may not reach till the end of the recording. So anyway, what is your question? Omega is the Casimir operator of K. A compactly supported function F, and to this function we have associated an operator on the Hilbert space. If you define the trace pi f of this operator, then it gives rise to a distribution on the group. Instead of V and W, let us take phi and phi prime and assume that phi is actually a k-finite vector of type delta. If you look at the right side of this equation here, the omega here is the Casimir operator of K, which acts as a scalar on any irreducible K type by that constant C delta. This formula should be valid for every integer, positive integer S. The sum of C delta to the power minus S, the sum over all irreducible K types, and for all Js, that is finite. That's a convergent summation. Yeah, that's true if you choose S to be sufficiently large. For example, if your representation of pi is square integrable, and so all the matrix coefficients will be square integrable, pi x phi inner product with phi prime as a function of the group G. That is square integrable. So both the functions there are square integrable because the first one is compactly supported. In addition, if you use the estimate for the multiplicity of a k-type delta and the fact that the dimension of delta is at most a certain polynomial on the highest weight of delta, one can deduce that pi f is of trace class. So this is the idea of defining the distribution character of an irreducible unitary representation. That is an invariant eigendistribution, and if chi omega is the infinitesimal character of omega, or chi pi is the infinitesimal character of pi, then this distribution will also have the same infinitesimal character when you differentiate by elements of the center of the enveloping algebra. You don't really need the fact that the matrix coefficients of pi are square integrable. What matters is the L1 norm of this omega SF. Harishchandra's study of that is because we use the Schwarz inequality for integrating the product of two L2 functions. Invariant eigendistributions begins by restricting attention to smaller invariant open sets. One such notion is what is called completely invariant open set. Later on, he introduces this notion of an elliptic class of invariant open sets, and to reduce questions about distributions to the study on smaller groups, smaller Lie subgroups of G, he introduces the notion of an adaptable pair V U. We will see these things in detail later on when we come to those. This adaptable pair is, there is one G invariant open set, and there is another invariant open set for a smaller group. An invariant open set V is said to be completely invariant if the semi-simple part of every element x of V in the Jordan decomposition belongs to V. Harishchandra's technique of proving his general theorems about distributions, that is, invariant distributions,
in a neighborhood of a semi-simple point A belonging to the group consists in transferring the study to an associated invariant distribution in a neighborhood of 0 of the centralizer of A in the Lie algebra G. This technique is often described as the method of descent. First, let us go through the statements of these theorems. So, theta is an invariant Z-finite distribution on V, where V is a completely invariant open set. Then theta is a locally summable function which is analytic on V intersected with the regular set G prime. Restrict this regular function theta to the regular points of a Cartan subgroup, multiply that by the well-denominator function delta LP for some choice of positive root system. The function phi LP is that product, and the differential equations enjoyed by that phi LP is described by this Harshchandra homomorphism mu GL. Suppose Z theta is the part of the center which annihilates the distribution theta. Think of the image of the center under the Harshchandra homomorphism to be constant coefficient differential operators on the Lie algebra L. Let F be the symbol F, German F, be the space of all C infinite functions in a neighborhood of 0 which are annihilated by the Z theta, where the exponential map from the Lie algebra to the Cartan subgroup, you can transport a small neighborhood of the regular element A in the Cartan subgroup to a small neighborhood of 0 in the Lie algebra. You should look at the map. H in the neighborhood going to A multiplied by the exponential of H. Then for each connected component of the small open neighborhood of the regular element A, there is a function in that space German F. These functions will vary from connected component to connected component. The next theorem analyzes this situation. In a connected component, in the set of regular elements in a small open neighborhood of an arbitrary point A of the Cartan subgroup, phi LP is an analytic function but depends on the connected components. But differentiate this phi LP by a differential operator on the Cartan subgroup. Which differential operator? This pi LP, work pi LP here. That work pi LP is the product of all the co-roots coming from the same positive roots, which was used to define this phi LP. When you apply this differential operator, that derivative extends continuously to all of the Cartan subgroup L intersected with our invariant open set, completely invariant open set V. It is also independent of the choice of the positive system. So you have an analytic function, different analytic functions on different connected components of set of regular elements, but they don't extend analytically to all of the Cartan subgroup. But you differentiate by a certain differential operator that extends continuously. And also, if you do it for two different Cartan subgroups, then they coincide on that continuous extension
coincides on the extension, no, on the intersection.
What is more, if you do the same thing for another Cartan subgroup L2, then that continuous extension of the derivative, continuous extension, coincides on the intersection of the two Cartan subgroups. The property is satisfied by an invariant eigendistribution described in theorem 1, and the continuous extension of a derivative on a Cartan subgroup described in theorem 2, they have a converse also. You need not even start with the distribution is defined on the group G, but just an invariant analytic function which is defined on the regular set, which is an eigenfunction for the action by the center. Then that analytic function theta prime is locally summable even around the non-singular points, provided you know that homomorphism of the center is given by a regular lambda. Okay, so let it be so, that is that eigenhomomorphisms even assumed to be regular. So you have this locally summable function on all of G, which defines an invariant distribution on all of G. But as a distribution, does it satisfy the differential equations coming from the center for the same eigencharacter? That need not happen. But if you, in addition, know that the derivative on a Cartan, the same derivative we considered in theorem 2, that derivative on any Cartan subgroup has a continuous extension, then the distribution is in fact an eigendistribution satisfies those central differential equations. That is the assertion in theorem 3. An element A of G, we are interested only in semi-simple elements. So an element A of G which is semi-simple is said to be semi-regular if the derived algebra of the centralizer of A in G, the Lie algebra G, has dimension 3.
So you know what's the derived algebra? That's, you take bracket with itself, that's the derived.
The statement in theorem 4 here is analogous to the if and only if statement of theorem 3. But this theorem avoids two assumptions which were made in theorem 3. It avoids the necessity to have regular homomorphism of the centers, that the eigenhomomorphism need not be regular. The second condition which it avoids is the continuous extension after applying the derivative with respect to 1 pi operator. But for the if and only if statement to go through, you only need to know that theta is good in the neighborhood of a semi-regular element, semi-simple element.
Okay. Now all this theorem, all these results about invariant eigendistributions, Harish Chandra was doing, it's taking a lot of time. It took several years for him. So for example, in 1955, he proved the regularity theorem, which he announced only 7 or 8 years later. But all these things happen over a long. What is this?
Now we come to this notion of an adapted system. Everything starts after picking a semi-simple element A in the group G. A is semi-simple. Consider those centralizers of the element A, both in the Lie algebra of G and in the group G. In the adapted system, U is an MA invariant open neighborhood of 0 in the Lie algebra.
Okay, why is it necessary here to say all this? I'll tell you why. There are some simple elements which are not regular, but if you look at the centralizer, that's if you take the derived algebra of that, that's going to be a smaller subalgebra, and so he wants to reduce questions about distributions on G to questions about distributions on equal rank subalgebras of smaller dimension. So that's why he sets up this definition of adapted pair.
You exponentiate U to get an open neighborhood of that would be a non-zero because 4 theorems we stated so far, and the next one, theorem 5, which we are going to formulate for these adapted systems. The point of view we should take is in the framework of differential geometric submersions. This map, which you see down below here, is an analytic submersion. The superscript G means conjugation by add G, conjugation by G. All these 3 manifolds, if you want to call it a manifold, all these 3 have an invariant non-zero exterior form of top degree. This map here is equivariant with respect to a group action by the group G. On the left here, there is left multiplication by the group element and on the first factor, and on the second factor, it is the trivial action, that is identity. On the right side on V, there is conjugation by group element. And this map is G equivariant. This Lie algebra MA here is in particular a vector space, and this IMA denotes the algebra of the symmetric algebra, the complex symmetric algebra on the vector space MA. But since it is a Lie algebra, there is also the enveloping algebra of the Lie algebra MA. There is a canonical isomorphism as algebras between the center of the enveloping algebra and the invariant elements of the symmetric algebra, that is denoted Z going to Z tilde. Well, here written zeta going to zeta tilde. Let V be a completely invariant open subset of G. For each semi-simple element A belonging to V, choose an adapted system UA VA in such a way that VA is contained in V. Once you have finished doing it for each semi-simple element A inside belonging to V, then this V is actually covered by all the VA here. We saw this analytical submersion map here down below just a little while ago. From a general differential geometric point of view, we mentioned that compactly supported functions on the left here by integrating over fibers gives a compactly supported function on the right. This association for function. Okay, so this is again saying that how to prove all these theorems, you view the whole picture in the framework of differential geometric subversions and you compare integration on one and the integration of the lifted function on the other. We'll do that integration and compare. There is a Jacobian coming into the picture. That is what these factors are about. The dA there, the J, those have to do with the Jacobian. Has a dual no, that's okay. Okay.